There is a hole in the clouds over the Philippine Sea right now, and it is 130 kilometers wide, a near-perfect circle of calm, drifting north toward Okinawa, visible from space to anyone with an internet connection. The last time the basin saw an eye like this, it was a Category 4 super typhoon called Kong-rey, and it tore into the eastern coast of Taiwan in October 2024. This one is only a Category 1, and that mismatch, a giant eye on a moderate storm, is exactly why the people who watch typhoons for a living are not sleeping much tonight. Tonight we walk what the eye actually means, where the storm is going, and why this one matters more than its category number says it should. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. The eye anyone can see from space. There is a hole in the clouds over the Philippine Sea right now, and it is 130 kilometers wide. You can see it from space. Anyone with an internet connection and a willingness to look at a satellite image can see it. A near-perfect circle of calm at the heart of an enormous spiral of moving cloud, dark blue against the white of the surrounding rain bands, sitting in the warm water about 600 kilometers south of Okinawa, drifting steadily north-northwest at the slow pace of a country highway. The circle is the eye. The cloud is the storm. The storm is Typhoon Jangmi, the 6th named system of the 2026 Western Pacific typhoon season, and at 3 o'clock in the morning Coordinated Universal Time on May 31st, the Joint Typhoon Warning Center in Pearl Harbor issued a prognostic reasoning bulletin that contained a single quietly remarkable measurement. The eye, the bulletin noted, has cleared to an unusually large diameter of 70 nautical miles. In the units most people think in, that is 130 kilometers across. To understand what that number means, you have to translate it into something you can hold in your head. 130 kilometers is larger than the entire land area of Greater London, inside the M25 motorway, which spans about 80 kilometers east to west. It is larger than the 23 special wards of central Tokyo measured corner to corner. It is approximately the distance from Manhattan to New Haven, Connecticut. It is, depending on how you slice it, about 3 times the diameter of a typical mature typhoon eye, which in the general case runs 30 to 50 kilometers across. If you took that calm circle of sky over the Philippine Sea right now and dropped it over the eastern seaboard of the United States, the entire borough of Manhattan, all 5 boroughs of New York City, and a good chunk of suburban Connecticut would fit inside it with room to spare. And that is just the calm part. The storm itself wraps around the calm in a ring of intense convection that extends hundreds of kilometers further outward. The reason this matters, the reason any of this matters at all, and not just as an interesting satellite picture, is that the last time a Western Pacific typhoon exhibited an eye of this scale was October 31st, 2024, when Super Typhoon Kong-rey came ashore on the eastern coast of Taiwan with an eye between 74 and 100 kilometers across and Category 4 sustained winds. Kong-rey was the largest storm to hit Taiwan in nearly 3 decades. It was the first typhoon in Taiwan's recorded history to make landfall after mid-October. It killed people. It caused billions of dollars in damage. It was a structurally enormous event that the meteorological community across the basin remembers very clearly, and it is what set the operational forecast community on alert when Jangmi's eye started clearing wider than expected over the last 48 hours. Here is the part of this that should make you sit up a little straighter. Kong-rey was a Category 4 super typhoon. Jangmi is a Category 1. The eye is comparable, the wind speeds are not, and that combination, a Category 4 eye structure on a Category 1 storm, is something that the people who do this for a living do not see often, and when they do see it, they pay very close attention to what happens next. This is not a documentary about a typical typhoon. The Western Pacific produces typhoons every year, sometimes 30 of them in a season, and the basin has a deep institutional memory of how those storms behave. This is a documentary about a typhoon that is doing something the basin recognizes but does not see often, headed straight for one of the most prepared and most exposed coastlines on Earth, during a week in which that coastline has already been dealing with a different kind of trouble entirely. By tomorrow evening, Japan Standard Time, the eye of Typhoon Jangmi will be making its closest point of approach to the island of Okinawa, passing just west of Kadena Air Base and the United States military installations there, sweeping across the Ryukyu archipelago with the kind of structural footprint that should belong to a much stronger storm. Then, over the following 3 days, It will recurve northeast around the subtropical ridge, accelerate along the southern coast of mainland Japan, sweep across the Kyushu industrial corridor, where a $14 billion semiconductor and automotive cluster sits exposed, and arrive at the Tokyo-Kanto Plain by June 4th as an extratropical system carrying the residual energy of the system it used to be. The forecast track is unusually confident. The forecast intensity is steady, not climbing. The forecast rainfall on the southeastern coast of mainland Japan is at least 400 millimeters over the duration of the event, with locally higher totals possible in the mountainous interior of Kyushu and Shikoku. The maximum significant wave height already measured in the southeastern quadrant of the storm is 10.4 meters, which is 34 feet of open ocean swell radiating outward from a system that has not yet made its closest approach to anything. The Joint Typhoon Warning Center confidence in the recurvature track is described as high through 3 days, medium beyond that. The Japan Meteorological Agency has been issuing typhoon advisories in close synchronization with JTWC since the system was upgraded to typhoon status at 6 o'clock Universal Time on May 30th. But none of that is the story. The story is the eye. The eye is what makes Jangmi different. The eye is what has the operational community paying extra attention. The eye is what is going to determine, over the next 48 hours, what kind of typhoon actually arrives on the Okinawa coast, and what kind of typhoon actually sweeps across the Japanese home islands after that. And to understand what that wide eye means, you have to understand what an eye is for, why a typhoon builds one, and why one this wide on a storm this strong is the kind of thing that makes meteorologists across 3 different basins stop what they were doing and start watching the satellite loops. It also matters because Okinawa and the broader Ryukyu archipelago is not a region that gets surprised by tropical cyclones. The Ryukyu Islands sit on the climatological highway of the western North Pacific typhoon basin, and the typical year delivers somewhere between 5 and 15 typhoon-class systems to within striking distance of the chain. The local infrastructure is built for it. The local population knows the drill. The local emergency management apparatus has decades of refined operational practice. When the population of Okinawa starts paying close attention to a typhoon, as it is paying close attention to Jangmi right now, that attention is not driven by unfamiliarity with the threat. It is driven by something else. It is driven by the structural anomaly, by the historical resonance with Kong-rey, by the concurrent seismic activity, by the unusual combination of features that this particular storm is bringing to a region that has seen many typhoons before, but rarely seen them quite like this. The attention is informed by experience, which makes the attention itself a meaningful signal about how unusual this event actually is. So let's go look at how a typhoon builds an eye. Part 2. How a typhoon builds an eye. A tropical cyclone is a heat engine. That is the cleanest one-sentence definition that any of the major textbooks of tropical meteorology will give you, and it is the right one to start with. The atmosphere over warm tropical oceans contains an enormous amount of latent energy in the form of evaporated water vapor. When that water vapor rises, cools, and condenses back into liquid droplets to form clouds and rain, it releases that latent energy as heat. A tropical cyclone is the structure that organizes that process into a self-sustaining, rotating, low-pressure system that can persist for days or weeks and travel thousands of kilometers across the open ocean. The warm water at the bottom is the fuel. The cold upper atmosphere is the sink. The rotating column of converging air is the engine. The eye is the chimney. You can think of the eye as the place where the engine has succeeded in spinning fast enough to create a column of subsiding air at its center. The intense convection of the storm is happening in a ring around the eye, in what meteorologists call the eye wall. The eye wall is the place where the maximum updrafts are happening, where the heaviest rainfall is being generated, where the strongest sustained winds are spiraling around the low-pressure center. In the eye itself, the air is sinking instead of rising. It is warming as it sinks. It is clearing as it warms. The eye is calm. The eye wall is the part that actually destroys things. This is critical to keep straight, because it is the geometric relationship between the eye and the eye wall that does most of the heavy lifting in understanding what Jangmi is doing. The strongest winds in any tropical cyclone live in the eye wall. The eye itself is calm, sometimes uncannily so, with blue sky overhead and a circle of towering cumulonimbus walls visible all around. When a typhoon's eye passes directly over you, you get the bizarre experience of a sudden lull, sometimes lasting for tens of minutes or even hours, before the second eye wall arrives from the opposite direction and the winds come back from the other side. People who have lived through it describe it as one of the strangest experiences in nature. The reason it happens is geometric. The eye is the calm. The eye wall is the wind. To get to the calm, the wind has to pass over you first. To leave the calm, the wind has to pass over you again. Now here is the part that most documentaries skip and that you genuinely need to understand to track what is happening with Jangmi right now. There is a general empirical relationship in tropical cyclone structure that says, broadly, that the most intense storms tend to have the smallest eyes. The reason is mechanical. A storm that is intensifying is contracting its inner core. The angular momentum that is being concentrated in the rotating column has to spin faster as the radius gets smaller, in exactly the same way that a figure skater pulling in her arms spins faster on the ice. The eye gets tighter. The eye wall winds get stronger. The pressure at the center drops. The most extreme version of this is what meteorologists call a pinhole eye, where a Category 4 or Category 5 super typhoon develops an eye that is only 10 to 25 kilometers across. Some of the most powerful storms in the recorded history of the Western Pacific Basin have had pinhole eyes at their peak intensity. Typhoon Haiyan in 2013, which devastated the central Philippines and killed more than 6,000 people, had an eye that contracted to under 20 kilometers at its most intense phase. Hurricane Wilma in 2005, which set the record for the lowest central pressure ever measured in the Atlantic Basin, had an eye that contracted to about 3 kilometers at one point, almost vanishingly small. That is the general pattern. Strong storms have small eyes. Weak storms have big eyes. Storms in transition have eyes of intermediate size. And the inverse correlation, while not absolute, is robust enough that the eye diameter is one of the structural diagnostics that operational forecasters use as a sanity check on intensity estimates. So when a Category 1 storm has an eye that would be more typical of a Category 4 super typhoon undergoing an eye wall replacement cycle, the forecasters notice, they have to notice. Because the relationship that holds in the general case has been violated, and the question becomes which of the small number of plausible explanations is actually operating in this particular storm. There are basically three candidate explanations for what Jangmi is doing structurally. The first is an eye wall replacement cycle. In a mature, organized tropical cyclone, an inner eye wall sometimes weakens and is replaced by a larger outer eye wall that contracts inward over time. During the transition, the storm temporarily exhibits two concentric eye walls, with the inner one shrinking and the outer one expanding inward to take its place. The intensity often dips during the replacement and then recovers, or exceeds the previous peak once the new eye wall consolidates. Jangmi may be in the middle of a replacement cycle, with the secondary eye wall now functioning as the new primary, and the inner eye consequently appearing wider than it would in a fully consolidated single eye wall configuration. The second is incomplete inner core compression. Not every storm reaches the tightly organized inner core that characterizes peak intensity Category 4 and 5 systems. Jangmi may simply be in a phase where the broader circulation has not yet had time to compress radially into a tighter eye, perhaps because the steering environment is moving the storm too quickly to allow full consolidation, or perhaps because the surrounding atmospheric conditions are providing the kind of marginally favorable, but not strongly favorable, environment that the JTWC discussion has been describing all week. The third is structural similarity to the so-called annular hurricane configuration, which is rare enough and important enough to deserve its own segment of this video. We're going to come back to that one in detail. For now, the operational reading is some combination of the first two. Most likely Jangmi has either completed an eye wall replacement cycle that left a wider secondary eye wall as the new primary, or it has not yet completed the inward radial compression that would tighten the eye to the more typical Category 1 range. The JTWC has noted in its discussions that no rapid intensification aids have triggered, which means the operational guidance is not currently projecting any sudden dramatic strengthening. The intensity model spread has converged tightly. The storm is forecast to maintain its current intensity through the closest approach to Okinawa and then begin a gradual weakening trend as it interacts with cooler sea surface temperatures and increasing wind shear north of the Ryukyu chain. But the eye is wide, and the eye being wide changes everything about how the storm interacts with land. Because the eye is the calm part, and the eye wall is the destructive part, and the wider the eye is, the wider the destructive ring is around it, and the longer the destructive ring takes to pass over any single point on the ground. We are going to come back to the geometry of that in a few minutes, and you are going to see the math, and you are going to understand why a Category 1 storm with a Category 4 eye structure is not the same hazard as a textbook Category 1 storm. But first, there is a body of peer-reviewed research that gave a name to what some of this looks like, and the name has been in the literature for over 20 years now, and it deserves a proper introduction. So let's talk about the annular hurricane. Part 3. The annular hurricane. In 2003, 3 researchers at the National Oceanic and Atmospheric Administration and Colorado State University published a paper in the journal Weather and Forecasting that gave a name to something the operational forecast community had been noticing for years, but had never had a clean technical vocabulary for. The paper was titled simply Annular Hurricanes, and it was written by John Naff, Jim Cossin, and Mark de Maria. It identified a relatively rare structural configuration of tropical cyclones that the authors had observed mostly in the Atlantic and East Pacific basins, but which the framework has since been applied to typhoons in the Western Pacific as well. The configuration has 3 defining features. The first feature is a symmetric circular eye, not an oval, not a tilted ellipse, not an asymmetric structure that bulges in one quadrant. A clean, almost geometric circle of calm at the centre of the storm, the kind of eye that you can almost trace with a compass on the satellite image. The second feature is a uniform thick eye wall surrounding the eye. The eye wall is roughly the same width all the way around, and it is thicker than the eye wall of a typical tropical cyclone of comparable intensity. The wind belt does not pinch in one quadrant and balloon out in another. It is a steady, structurally uniform ring. The third feature is a notable absence of outer spiral banding. A typical mature tropical cyclone exhibits multiple curving spiral bands of convection, extending hundreds of kilometers outward from the eye wall, organized in a roughly logarithmic pattern that any photograph of a hurricane shows clearly. Annular hurricanes lack most of that outer banding. The convection is concentrated in the central eye wall ring, with very little organized rainband structure beyond it. When you put those 3 features together, what you get is a storm that looks visually distinctive. It looks bigger and more symmetric than a typical hurricane of the same intensity. It looks, in the words of one veteran satellite analyst, more like a buzzsaw than a spiral, and it behaves differently from a typical storm too, which is what makes the framework operationally important. Annular hurricanes tend to be unusually steady state. They do not undergo rapid intensification or rapid weakening in the way that other tropical cyclones often do. They tend to hold their peak intensity for longer windows than the general statistics would predict. The operational consequence of this is that when forecasters see a structure that looks even partly annular, they get more cautious about projecting weakening. The storm may simply hold its intensity longer than the environmental analysis would suggest, because annular configurations have an internal stability that resists external perturbation. Annular hurricanes also tend to be larger in their wind footprint than would be predicted from their central pressure alone. A pressure-wind relationship is one of the standard diagnostics that forecasters use to estimate intensity from observable measurements. Annular storms tend to systematically violate that relationship in the direction of having broader wind fields than their pressures predict. The maximum sustained winds are not necessarily higher than a textbook storm at the same pressure. They are distributed over a wider geographic footprint. Now, Jangmi is not a textbook annular hurricane. It still has some outer banding structure visible in the satellite imagery, which a strict annular system would lack. The thermal structure at the upper levels is not quite as symmetric as a fully annular configuration would require, but it shares the symmetric circular eye, and it shares the steady-state behavior. The JTWC discussions all week have noted the tight convergence of the intensity guidance and the absence of any rapid intensification signal. The storm has been holding its intensity in a way that is not characteristic of a typical Category 1 typhoon, which would normally be either intensifying further or beginning to weaken as it approached the marginally favourable upper-end environment that the discussions have described. The annular hurricane framework matters here because it gives the operational community a published, peer-reviewed vocabulary for what they are seeing. It is not just a curious satellite picture. It is a recognised structural configuration with documented consequences for how the storm behaves over the next 24 to 48 hours. The fact that Jangmi is not a textbook annular system, but shares the eye and the steady intensity profile means that the operational discussions are now incorporating annular class reasoning into their analysis, which is a polite way of saying that the forecasters are being more cautious about predicting weakening and more attentive to the possibility that the storm holds its intensity all the way through the Okinawa interaction rather than degrading on the approach. The annular framework is what gives us the language to describe what Jangmi is doing and what it implies for how the storm will arrive. A Category 1 typhoon with annular-class structural features arriving on the Ryukyu coast is a different operational hazard than a textbook Category 1 typhoon arriving on the same coast. Same wind speeds, different footprint, different duration, different damage geometry. We're going to walk through the geometry in detail in a few minutes, but first we need to understand where this storm is actually going, because the track is what determines who feels it, and when. So let's look at the track. Part 4. The track through the subtropical ridge. If you want to understand where any Western Pacific typhoon is going, you have to look up at the atmosphere above it. A tropical cyclone is a heat engine at the surface, but it is also a feature embedded in the larger atmospheric circulation, and the larger atmospheric circulation is what decides where the storm goes. The dominant feature steering Jangmi right now is the subtropical ridge, which is a semi-permanent zone of high pressure that sits across the central Pacific north of the storm. Subtropical ridges are not stationary features. They expand, contract, drift, and reform throughout the seasons, in response to the global pattern of heating and cooling. But on the timescale of a single typhoon's lifetime, the ridge is essentially a fixed feature whose position and amplitude determine the trajectory of any cyclone moving underneath it. Jangmi is currently being steered north-northwestward by the eastern flank of the subtropical ridge to its northwest. The flow on the southern side of a high-pressure system circulates clockwise, which means that a storm sitting south of the ridge gets pushed westward, and a storm sitting on the southeastern flank gets pushed in a north-northwestward direction. That is exactly the direction Jangmi has been moving for the last 72 hours. The storm has been drifting north-northwest at about 15 to 20 kilometers per hour, slow but steady, with very little variation in the heading. The forecast over the next 24 hours continues that pattern. Jangmi will keep moving north-northwest under the steering influence of the ridge. It will pass over warm water that should allow it to maintain its current intensity. The eye, whatever shape it ends up holding through the next eyewall cycle, will continue to track north-northwest in the satellite imagery. But then, after about 24 hours from the most recent advisory, something changes. The subtropical ridge starts to migrate. The mid-latitude westerlies, the band of west to east upper-level flow that defines the boundary between the tropical and extratropical atmospheres, starts to expand southward and exert its own steering influence on the storm. Jangmi finds itself in the transition zone between two competing steering regimes. The clockwise circulation of the receding subtropical ridge is no longer the only steering signal. The eastward push of the approaching mid-latitude westerlies is starting to take over. What happens at the transition is the recurvature, the storm hooks. Its heading rotates from north-northwest through north-northeast, and eventually settles on a northeastward track that carries it parallel to the southern coast of mainland Japan. This is the classic recurving Pacific typhoon trajectory. It is the most common large-scale steering pattern for storms that originate in the Philippine Sea during the warm months. It is the trajectory that Typhoon Hagupit followed in 2020. It is the trajectory that countless August and September Pacific typhoons have followed in the historical record. The recurvature is what defines a Japanese impact storm versus a Taiwan impact storm versus a Korean impact storm. The position and timing of the recurvature determines which coastline gets hit and how hard. For Jangmi, the recurvature is forecast to begin shortly after the storm reaches its closest point of approach to Okinawa, which the JTWC has placed at about 9 o'clock in the morning, Coordinated Universal Time on June 1st. In Japan Standard Time, which runs 9 hours ahead of UTC, that is 6 in the evening local, so the closest approach is Monday evening in Okinawa. The eye, which by then will either have tightened through its eyewall replacement cycle or held wide depending on what happens internally over the next 36 hours, will pass just west of Kadena Air Base, which is the major United States military installation on the central part of the main island. The centre of the storm will not actually cross the island. It will track just offshore to the west, but the eyewall will sweep across the island, and the eyewall is what carries the damaging winds. After the closest approach to Okinawa, the recurvature accelerates the storm to the northeast. Over the next 24 hours it transits the Amami Islands, the chain of smaller Japanese islands northeast of Okinawa that act as the first land interaction for any recurving Pacific typhoon headed toward Kyushu. By Tuesday into Wednesday Japan time, the storm is approaching Kyushu itself, the southwesternmost of the 4 main Japanese home islands. By Wednesday into Thursday, it is sweeping along the southern Pacific coast of Honshu, the largest of the Japanese islands headed northeast on a track that parallels the coast. By Thursday, June 4th, the system is approaching the Tokyo-Kanto plain, where it is forecast to begin completing extratropical transition. By Friday, June 5th, the storm has fully transitioned to an extratropical low-pressure system and is exiting northeastward into the open northwest Pacific. The remarkable thing about this forecast is how confident it is. The JTWC has placed the cross-track spread, which is the standard measure of forecast uncertainty, in the direction perpendicular to the motion of the storm, at 120 kilometers at 3 days out and 185 kilometers at 5 days. To put those numbers in context, the 5-year basin average cross-track error for Western Pacific typhoons is approximately 175 kilometers at 3 days and 290 kilometers at 5 days. Jangmi's forecast spread is significantly tighter than the climatological average. The track guidance is in unusually solid agreement across the deterministic models. The European model, the American GFS, the Japanese model, and the various ensemble systems are all converging on essentially the same recurvature trajectory, with very little spread between them. When forecast confidence is this high, it means something specific. It means the steering environment is sufficiently well defined and stable that the various models are extracting essentially the same atmospheric signal from the same global observational data. The subtropical ridge position is locked in. The mid-latitude westerly intrusion is locked in. The recurvature timing is locked in to within hours. The storm is going to do what the consensus says it will do, give or take about 100 kilometers in any direction. Which means we know, with high operational confidence, that within the next 40 hours the eye of Typhoon Jangmi will pass within sight of Okinawa. We know that within the next 60 hours it will be brushing Kyushu. We know that within the next 100 hours it will be approaching Tokyo. We know which coastline will feel the storm, and roughly when. The thing we do not yet know with the same confidence is exactly what the storm will feel like at landfall, because the storm's structural anomaly, the wide eye, the partly annular configuration, the steady-state intensity, means that the wind footprint at any given moment is wider than the category number would suggest, and the duration of the maximum sustained winds at any single point under the eye wall is longer than the category number would suggest. That is the geometry we have to walk through next, the math of why a wider eye hurts more. Part 5. Why the wider eye hurts more. Let's do the geometry carefully, because the geometry is the part of this story that most coverage skips, and the geometry is what determines what the storm actually does when it arrives. A typhoon's destructive winds live in the eye wall. The eye wall is a ring. A ring has a circumference. The circumference depends on the radius. For a circle with a radius of 15 kilometers, which would correspond to a 30-kilometer eye, the circumference is about 94 kilometers. For a circle with a radius of 65 kilometers, which corresponds to Jangmi's 130-kilometer eye, the circumference is about 410 kilometers. That is a ratio of more than 4 to 1. The Jangmi eye wall is distributing its destructive winds over a ring of cloud that is more than 4 times longer than the eye wall of a typical 30-kilometer-eyed storm. The first operational consequence of this is that the geographic area swept by the destructive eye wall at any single moment in time is much larger for the wider-eyed storm. If you imagine the eye wall as a brush painting a swath of damage across a coastline as the storm moves over land, the brush of the Jangmi eye wall is roughly 4 times wider than the brush of a typical Category 1 eye wall. More of the coast feels the maximum winds at once. The wind footprint at peak intensity is geographically wider. The second operational consequence is more subtle, but actually more important. It has to do with the duration of the maximum sustained winds at any single point on the ground. Imagine you are standing in central Okinawa as the eye wall of Jangmi approaches. The storm is moving north-northwest at about 25 kilometers per hour. The eye wall has a thickness, but for the purpose of this calculation, let's consider the time it takes for the outer edge of the eye wall on one side of the eye to pass over you, followed by the calm of the eye, followed by the inner edge of the eye wall on the other side. The total distance the storm has to travel for that complete passage is approximately equal to the diameter of the eye plus 2 eye wall thicknesses. But the eye wall thickness is small compared to the eye, so to first approximation, the duration of the eye wall passage is just the diameter of the eye divided by the forward translation speed of the storm. For a storm with a 30-kilometer eye moving at 25 kilometers per hour, the eye passage takes about 1¼ hours. For a storm with a 40-kilometer eye moving at 25 kilometers per hour, it takes about 1½ hours. For a storm with a 130-kilometer eye moving at 25 kilometers per hour, it takes about 5¼ hours. 5¼ hours. That is what it means for a Category 1 typhoon to have a Category 4 eye structure. The geographic area that experiences the maximum sustained winds gets, in addition to that geographic area being 4 times larger, also more than 3 times the duration of exposure compared to a typical storm of the same intensity. 5 hours of sustained 90 to 100 km per hour winds is a fundamentally different hazard than 90 minutes of the same winds. The structural engineering damage scales non-linearly with duration. Roofs that survive 90 minutes can fail at 5 hours because the cumulative loading on fasteners, the cumulative fatigue on metal panels, the cumulative damage to seals and trim eventually exceeds the design tolerance. Trees that hold for 2 hours come down in 4. Power lines that flex through brief gusts work harden and snap under sustained loading. The longer the exposure, the larger the share of marginal infrastructure that fails. The third operational consequence is the storm surge geometry. A typhoon generates storm surge by pushing seawater ahead of itself, with the height of the surge depending on the wind speed, the duration of the wind, the geometry of the coastline, and the bathymetry of the nearshore seafloor. The wider the wind field, the wider the swath of coastline that experiences surge generation, and the more total volume of water is being pushed ashore at any given moment. A wider eye does not by itself produce a higher peak surge for a given wind speed, but it does produce a wider geographic distribution of significant surge, which means more coastline experiences inundation, more infrastructure is exposed to storm surge flooding, and the cumulative damage from the surge is distributed across a larger area than a textbook Category 1 would produce. There is a historical analogy that is worth holding in mind here. In 1992, Hurricane Andrew came ashore in southern Florida as a Category 5 storm with a pinhole eye. The eye was very small, maybe 10 to 15 kilometers across. The wind belt was concentrated in a narrow ring. The damage was catastrophic in a relatively narrow corridor immediately under the eye wall, but areas just 20 or 30 kilometers north and south of the eye experienced significantly less damage. Andrew was an extreme example of a small, intense focus storm. The compass image of Andrew on the satellite map is essentially a tight spiral around a dot. Now compare that to Typhoon Tip in 1979, the largest tropical cyclone ever observed on Earth, which had a circulation diameter of more than 2,000 kilometers and an eye that varied between 60 and 120 kilometers across through its life cycle. Tip's peak intensity was actually higher than Andrew's, but the wind footprint was distributed across an area larger than the entire continental United States east of the Mississippi. Tip never made a major landfall, but if it had, the damage geometry would have been completely different from Andrew's. Wider footprint, longer exposure, more total surface area swept by destructive winds, even if the peak winds at any single point were comparable. Jangmi is not Tip. It is not even close to Tip's scale, but it shares the structural feature of distributing its winds over a wider footprint than the category number would predict, and that is the feature that is going to determine how Okinawa feels the storm tomorrow evening. The way to think about it is this. A textbook Category 1 typhoon arriving on Okinawa would be a familiar event. The Ryukyu Islands get them several times a season. The infrastructure is built for them. The population knows how to prepare. The buildings hold. The aftermath is manageable. A Category 4 Super Typhoon arriving on Okinawa would be a very different event, a once-in-a-decade catastrophe of the kind that requires extensive post-event reconstruction. A Category 1 typhoon with a Category 4 eye structure is something in between, and the exact location on that spectrum is determined by the geometry and the duration of the eye wall exposure. The Joint Typhoon Warning Center forecast has the closest approach, winds at 100 km per hour, which is solidly in the Category 1 range. The Japan Meteorological Agency has the central pressure at the closest approach, near 982 hectopascals, also Category 1. Those numbers are correct, by the standard intensity metrics, but the geometry of the eye wall means that those winds are going to be felt over a wider area for a longer duration than the metrics alone would suggest. The damage envelope is going to be wider than a textbook Category 1. This is the central operational reality that the forecast community is working with right now. Category 1 winds, Category 4 spatial distribution. 5 hours of exposure to maximum sustained winds for the population sitting beneath the eye wall path. A storm that hits harder, for longer, across a wider area than its category number says it should. And that is what is about to arrive on Okinawa. To anchor the geometry in something visual, picture a roundabout in a major city. A textbook Category 1 typhoon eye wall is like a small traffic circle, maybe 30 meters across, that you drive around in 15 seconds. The Jangmi eye wall, scaled to the same imaginary city, is more like a multi-lane orbital highway that takes 10 minutes to circumnavigate at city speed. Same concept, vastly different scale. The traffic circle and the orbital highway both produce the same kind of curved motion, but the scale at which they affect everything around them is fundamentally different. A car driving around the traffic circle is a brief interruption in normal traffic flow. A car merging onto the orbital highway is committing to a much longer engagement with the road. The geometry shapes the experience. The same is true for an eye wall sweeping across a coastline. The narrow eye wall is a brief interruption. The wide eye wall is a sustained engagement. The infrastructure beneath the wide eye wall has to manage a fundamentally different loading profile than the infrastructure beneath the narrow one. There is one more piece of the geometry that is worth understanding before we move on, because it changes how the winds actually arrive at any given point under the eye wall. The eye wall is a ring of intense convection that surrounds the eye, but the winds within the eye wall are not uniform around the ring. The strongest winds are typically found in the right front quadrant of the storm relative to its direction of motion, because the forward motion of the storm adds to the rotational velocity on that side and subtracts from it on the opposite side. For a storm moving north-northwest at 25 km per hour, the strongest winds will be in the northeast quadrant of the eye wall. For the same storm after a curvature has rotated its heading to northeast, the strongest winds will be in the southeast quadrant. The exact quadrant of maximum winds shifts as the storm changes direction, which means the geographic distribution of damage along the track is not symmetric. The right side of the track gets hit harder than the left side, with the asymmetry magnified by the wider footprint of the wider eye wall. For Jangmi specifically, this means that the most intense impact on Okinawa is going to be felt by the eastern half of the main island, as the storm passes just to the west. The eastern coast of Okinawa, including the major population centres along Highway 329 and the areas around Aruma City and Okinawa City, is going to experience the right front quadrant of the eye wall as the storm transits. The western coast, including Naha, will experience somewhat less intense conditions because it sits on the weaker left front side of the track. Both sides will experience damaging winds. The asymmetry just determines how the damage is distributed between the two coasts. After Okinawa, when the storm recurves northeast and tracks along the southern Japanese coast, the right front quadrant shifts to the southeast. That means the southeastern coasts of Kyushu, Shikoku, and Honshu will experience the strongest winds as the storm sweeps past. The southwestern coasts, sheltered on the backside of the track, will experience somewhat less intense conditions. This is the standard geometric pattern for a recurving Pacific typhoon, and the wider footprint of the Jangmi configuration means that the asymmetric damage envelope along the right front side will be distributed over a larger area than a textbook event would produce. That is the full geometry. The wider eye, the longer eye wall passage, the asymmetric quadrant distribution, the right front side of the track taking the worst of the impact. All of those features apply at every landfall and near landfall along the storm's track over the next 4 days. The eastern coast of Okinawa tomorrow, the eastern coast of Kyushu on Tuesday, the southeastern coast of Shikoku on Wednesday, the southeastern coast of Honshu on Wednesday into Thursday, the eastern flank of the Tokyo-Kanto Plain on Thursday into Friday. Each of those coastlines will experience the right front quadrant of the storm as it passes, and each of those coastlines will experience the structural anomaly we have been describing throughout this analysis. Part 6. Okinawa goes to T-Core 2. On the afternoon of May 30th, United States military installations across Okinawa Prefecture issued an internal status change. The status was Tropical Cyclone Condition of Readiness 2. In military operational language, T-Core 2 means destructive winds of at least 58 miles per hour, which is about 93 kilometers per hour, are anticipated within 24 hours. The condition is the second highest level in a 5-step preparation framework that runs from T-Core 5 at the calmest end through T-Core 1 caution, 1 emergency and 1 recovery as the storm approaches and passes. Kadena Air Base entered T-Core 2, Camp Foster entered T-Core 2, Camp Hansen, Camp Schwab and Marine Corps Air Station Futenma all entered T-Core 2. Across the broader United States Forces Japan footprint on the island, the operational preparation rhythm shifted from routine standby to active typhoon approach posture in a matter of hours. What Tikor 2 means in practice is a checklist of preparation actions that have to be completed before the next condition step. Outdoor equipment gets secured or moved indoors, loose construction materials get tied down or removed, personnel get reminded of the shelter-in-place protocols, aircraft on the flight lines either get evacuated to other bases on the mainland or get rolled into the hardened shelters. Medical and emergency response teams check their equipment readiness. Communications relays get verified. Fuel stocks for backup generators get topped off. By the time the condition steps up to TCCOR 1, which happens when destructive winds are anticipated within 12 hours, the bases are essentially locked down, with only essential personnel moving between buildings and the population sheltered in place. This is a familiar rhythm. The United States military has been operating in Okinawa since 1945, and the Typhoon Preparation Framework is one of the oldest and most refined operational protocols in the Pacific Theater. The bases on Okinawa typically execute T-Core transitions 5 to 15 times per typhoon season, depending on how many storms approach close enough to require preparation. The institutional muscle memory is deep. Every base commander, every shift supervisor, every senior enlisted leader has done this many times before. What is different about Jangmi is what we have been talking about for the last several minutes. It is not the wind speed, it is the structural footprint. The T-Core rhythm is built around the assumption that a Category 1 typhoon delivers Category 1 winds for a Category 1 duration over a Category 1 geographic footprint. The preparation actions are calibrated to that assumption. The shelter-in-place protocols are built for that envelope. The post-event damage assessment is staffed for that scale. When the actual storm delivers Category 1 winds but for 3 times the duration, and across a 4 times wider footprint, the preparation framework still applies, but the post-event reality may exceed what the framework was designed to handle. The bases are not the only population at risk. Okinawa Prefecture has a permanent population of approximately 1.5 million people, the vast majority of them Japanese civilians who live on the main island and in the smaller islands of the surrounding archipelago. Those residents are also preparing. The Japan Meteorological Agency has been issuing typhoon advisories since the storm was first identified, and the advisories step up in intensity as the storm approaches. By Sunday evening Japan time, the advisories will be in their most active phase, with public broadcast warnings, transportation suspension notices, and the standard package of pre-typhoon preparation guidance that is familiar to anyone who has lived through a typhoon season in southern Japan. The first ripple of commercial disruption has already begun. The Hong Kong-based budget airline HK Express has cancelled 6 flights to and from Okinawa over the next 2 days. That is a small number, but it is the leading edge of what will become a much larger pattern over the next 48 hours. By Monday morning Japan time, most commercial aviation into and out of Okinawa will be suspended. The major airlines, Japan Airlines and All Nippon Airways, will be issuing waiver and rebooking notices. The cruise ships that operate in the Ryukyu region will be diverted. The ferries that connect the smaller islands to the main island will be in port. The port of Naha will be closed to commercial shipping. This is the operational rhythm that any tropical cyclone of meaningful intensity triggers in southern Japan. It is well rehearsed, it will execute on schedule. The question is not whether Okinawa can handle a typhoon. The question is whether the storm that arrives is the storm the preparation framework was built for, or whether the structural anomaly we have been describing produces an event whose footprint exceeds the assumptions baked into decades of local emergency planning. The honest answer is that we do not yet know, and the people who would know are the people who are watching the satellite imagery and the surface observations over the next 24 hours. The eye structure may contract through a secondary eye wall consolidation, tightening the wind footprint to something closer to the textbook Category 1 envelope and reducing the duration of the maximum sustained winds at any single point. Or the eye structure may hold wide, in which case the storm that arrives on Okinawa is the storm we have been describing. Or some intermediate evolution may produce some intermediate outcome. The next 24 hours of satellite microwave passes will tell the forecasters which scenario is unfolding, and the operational community will adjust the advisories accordingly. For now, the rhythm is set. The bases are at Tikor 2. The civilian preparation is underway. The advisories are stepping up. The flights are getting cancelled. The ferries are coming in. The ports are getting buttoned up. Okinawa is doing what Okinawa knows how to do. There is also a layer of preparation that is happening in the civilian community that is worth understanding, because it is one of the most distinctive features of how southern Japan handles tropical cyclones. In Okinawa, The typhoon preparation rhythm extends beyond the standard checklist of securing outdoor items and stocking up on supplies. Local convenience stores stock specialized typhoon preparation kits that include emergency lighting, portable radios with batteries, packaged water, ready-to-eat meals, and waterproof document pouches. Many older buildings have permanent typhoon shutters installed on the windows, the kind that roll down from concealed housings above each opening, and which have been part of the architectural vocabulary of Okinawan construction for decades. The newer concrete construction that has dominated since the post-war rebuilding period is rated for higher wind loads than the lumber and tile construction that was destroyed in some of the major mid-century typhoon events. Okinawa, more than almost any other populated region in Japan, has built its housing stock around the certainty that significant typhoons will arrive multiple times per generation. The school system has its own typhoon protocol. When a typhoon is forecast to affect the region during a school day, the Okinawa Prefectural Board of Education issues a closure decision based on the timing of the storm's expected arrival. Relative to the start of the school day, the wind speed forecasts at the time students would be commuting and the duration of expected impact. Schools closed in advance, with the closure decision communicated through the standard public broadcast channels and through the school's own parent notification systems. For an event like Jangmi, which has been forecast for several days, the school closure decisions are typically made the evening before so that families have a full overnight window to adjust childcare arrangements and commuting plans for adults who would normally drop off children before going to work. The medical system has its own typhoon protocol. Hospitals across Okinawa Prefecture have continuity of operations plans that include on-site generator capacity for extended grid outages, redundant water supply systems, pre-positioning of essential medical supplies, and patient triage protocols for the period when emergency response capability is reduced due to the storm. The major hospitals on the main island, including the Okinawa Prefectural Chubu Hospital and the Naha City Hospital, have decades of experience operating through typhoon impacts and have rehearsed protocols for everything from elective surgery scheduling to discharge planning to emergency department staffing through the storm window. The smaller clinics and outpatient facilities follow the lead of the major hospitals in establishing operational continuity during the storm. What Okinawa cannot do, what no preparation framework anywhere can do, is change the structure of the storm that is bearing down on it, and in this particular case, the storm that is bearing down on Okinawa is one with a 130-kilometer eye, sustained winds in the Category 1 range, the steady-state behavior of a partly annular configuration, and the operational confidence that it will arrive on schedule, on track, at the closest point of approach, by tomorrow evening Japan time. There is one more layer to this story before we get to the geographic targets further along the track. Because Okinawa, as anyone who has been following the regional news for the last 2 weeks knows, is not arriving at this typhoon from a position of operational rest. The last 14 days have been unusually active for southern Japan, and not just in the atmosphere. So let's talk about what else has been happening. Part 7. Okinawa can't catch a break. On May 20th, 11 days before the typhoon began its closest approach run, the ground in Kagoshima Prefecture moved. The Japan Meteorological Agency recorded the event as a magnitude 5.9 earthquake centered in the Kagoshima Islands, the chain of smaller volcanic islands south of the main Kyushu landmass that includes the Takara Group and the Amami Archipelago. The shaking was felt across the Takara Islands and southern Kyushu. There were no significant casualties and no major structural collapses, but the event was strong enough to be the lead seismic story across Japanese national news on the day it happened. A magnitude 5.9 is not a catastrophic earthquake by Japanese standards. Japan has, in any given year, dozens of events in that magnitude range. But it is large enough to be felt by every person within 100 kilometers of the epicenter, large enough to shake glassware off shelves, large enough to register on the public emergency broadcast network. It got people's attention. 9 days later, on May 29th, a smaller event registered closer to Okinawa itself. The Japan Meteorological Agency recorded a magnitude 4.2 earthquake near Kumijima, a small island about 100 kilometers west of the main Okinawa island. The event was at a depth of 230 kilometers, which is unusually deep. It was an intermediate depth slab event within the descending Pacific lithosphere beneath the Ryukyu Trench, not a shallow crustal event near the surface. Earthquakes at that depth, even at modest magnitudes, are felt over a wider geographic area than shallow events because the seismic waves propagate efficiently through the mantle. People in central Okinawa felt the shaking. The event made the local Japanese press. It did not make international news. 10 days before the Kumajima event on May 19th, the United States Geological Survey had recorded a magnitude 4.4 earthquake about 84 kilometers northeast of Ishigaki in the southwestern Okinawa archipelago at a depth of 101 kilometers. Another intermediate depth slab event. Another widely felt but locally non-destructive shake. Another news item in the Okinawan press that came and went without making the international news cycle. None of these three earthquakes is, individually, a particularly significant event. The Ryukyu Trench is one of the most seismically active plate boundaries on Earth. The descending Philippine Sea plate is grinding underneath the Eurasian plate at a rate of about 7 centimeters per year, and the resulting seismicity is constant. The southern Japanese island arc records hundreds of magnitude 3 and 4 events per year, dozens of magnitude 5 events, and a handful of magnitude 6 events in most years. By the standards of the basin, a magnitude 5.9 followed by 2 magnitude 4 class events in a 10-day window is well within the normal background variability. There is no statistical signature suggesting a regime change. The events are not foreshocks of a larger pending event. The seismological community is not on the record expressing elevated concern about the southern Japanese region as a result of this short-term cluster. But here is what is happening anyway. The people who live in the Ryukyu Islands and southern Kyushu have noticed. The social media discourse around the typhoon's approach has, over the last few days, started to incorporate a framing that one observer described simply as Okinawa can't catch a break. The framing is emotionally legible, it is geographically accurate, it is operationally significant, and it is causally wrong. It is causally wrong because there is no peer-reviewed mechanism by which a magnitude 5.9 deep-focus earthquake in Kagoshima can influence the formation of a tropical cyclone over the western Philippine Sea, 2,000 kilometers away. There is no mechanism in either direction. The earthquakes and the typhoon share a regional geography, because both are products of the same plate tectonic and climatological context. Okinawa sits on the leading edge of the Eurasian plate above the Ryukyu Trench. The descending Philippine Sea plate produces the seismicity. Okinawa also sits in the climatological corridor of Western Pacific typhoon recurvature. The subtropical ridge and the warm Philippine Sea produce the cyclones. The two phenomena coexist in the same region for completely different reasons, and the events are statistically independent. The compound observation is real. The coordinated event claim has no underlying mechanism. But here is the part that does matter. That is not just a debunking of an internet framing, but an actual operational reality that the emergency management community is taking seriously. The Japan Meteorological Agency manages both classes of hazard through the same regional offices. The same forecasters who are tracking the typhoon approach are also processing the seismic data from the Kagoshima cluster and the Kumajima event and the Ishigaki event. The same public warning infrastructure, the same broadcast emergency information channels, the same evacuation coordination systems, the same disaster medical response teams are being asked to maintain readiness across two different categories of hazard during the same week. The cognitive load on the regional emergency management apparatus is elevated. The cognitive load on the residents themselves is elevated. The compound event framing may be causally wrong, but it is operationally meaningful because the population is being asked to track two different threat signals in parallel during a high-attention 48-hour window. This is the part that often gets lost in the debunking. When you point out that the earthquakes did not cause the typhoon, and the typhoon will not trigger more earthquakes, you have said something that is true and important, but you have not addressed why the compound event observation feels meaningful to the people experiencing it. It feels meaningful because the experience of stacking concurrent hazards is real. It feels meaningful because the operational reality of preparing for multiple simultaneous threats is real. It feels meaningful because the historical memory of southern Japan, which includes the 1995 Kobe earthquake and a continuous record of typhoon impacts going back centuries, knows that the region has compound vulnerability in its bones. The internet framing of Okinawa can't catch a break is wrong about the mechanism but right about the lived experience. What it means operationally for the Jangmi event specifically is that the regional emergency management posture is more alert than it would be for a typhoon arriving on a coastline that had not just experienced 2 weeks of moderate regional seismicity. The shelters are open earlier. The evacuation guidance is more emphatic. The pre-event communications are more frequent. The post-event damage assessment teams are pre-staged in a wider geographic distribution than they would be for a routine typhoon approach. The medical response capacity is elevated. The whole regional system is leaning forward more than it normally would, and on top of that posture, the structural anomaly of the storm is arriving. A Category 1 typhoon with the eye structure of a Category 4 Super Typhoon. 5 hours of sustained Category 1 winds at any single point under the eye wall. A wind footprint 4 times wider than the textbook envelope. A population whose cognitive bandwidth has been split by 2 weeks of concurrent seismic attention. The arrival is going to be unusual. The response is going to be unusual. The post-event accounting is going to be unusual. There is a piece of context here about the Japan Meteorological Agency itself that is worth understanding, because the JMA is one of the most institutionally sophisticated national meteorological services in the world, and the way it manages compound hazard windows is genuinely impressive even by international standards. The JMA was established in 1875, making it one of the oldest continuously operating meteorological agencies on Earth. Over the intervening 150 years, it has built a national observation network of weather radar stations, surface weather stations, upper air sounding stations, ocean buoys, satellite ground stations, and seismograph stations that together produce a continuous real-time picture of the atmospheric and seismic state of the Japanese archipelago and the surrounding ocean basins. The agency operates the world's largest national seismograph network, with thousands of strong motion and broadband instruments distributed across every populated region of the country. It operates its own constellation of geostationary weather satellites, the Himawari series, which provide continuous imagery of the Western Pacific Basin at higher temporal resolution than any other satellite system covering the same geography. It runs operational numerical weather prediction models in-house, including the JMA Global Spectral Model and the Mesoscale Model, which produce track and intensity forecasts that are tightly coupled with the JTWC products and which serve as the primary operational guidance for the Japanese government's typhoon preparation and response. When the JMA manages a compound hazard window, like the one currently active in the Ryukyu chain, it does so through an integrated communications architecture that includes the Public Broadcast Emergency Information System, the Prefectural and Municipal Emergency Management Offices, the School System Communications, the Transportation System Coordinators, and the various industry-specific protocols that the major Japanese sectors maintain. The system has been refined over decades of operational practice and has been tested through some of the most severe natural disaster events of the post-war era, including the 1995 Kobe earthquake, the 2011 Tohoku earthquake and tsunami, and the various typhoon events that have shaped the development of the modern Japanese disaster response framework. The reason this matters for Jangmi specifically is that the JMA's institutional capacity is what allows the Japanese system to absorb compound hazard windows without the kind of cascading operational failures that less sophisticated meteorological services have sometimes experienced. The seismic events of the past 2 weeks have been processed by the same agency that is now managing the typhoon advisory cycle. The public communications about both classes of hazard are coming from the same integrated source, which means that the population is not receiving contradictory signals from competing agencies. The school closure decisions, the transportation system suspensions, the industrial response coordination, all of them are running through institutional pipelines that have been built specifically to handle exactly this kind of compound hazard scenario. What this means in practice is that the elevated operational load we have been describing is being absorbed by a system that is institutionally designed to absorb it. The JMA can do this. It has done it many times before. The current event is not novel in its compound character, it is novel in the structural anomaly of the typhoon component, and the seismic component is well within the routine background variability of the basin. The system's capacity to manage the integrated response is not what is being tested by Jangmi. What is being tested is the question of how the storm itself behaves at landfall, given its unusual structural configuration. The structural anomaly in the eye is arriving on a coastline whose seismic preconditioning has already loaded the operational and cognitive systems before the storm even arrives. That is what Okinawa is bringing to the storm. That is what the storm is bringing to Okinawa. And both halves of that equation are happening for reasons that have nothing to do with each other and everything to do with the geography of one of the most exposed island chains on the surface of this planet. There is one other reason the operational community is paying as much attention to Jangmi as it is, and the reason has a name and a date. The name is Kong-rey. The date is October 31st, 2024. That is the storm we have to look at next, because Kong-rey is the most recent case study the basin has for what a large-eyed Pacific typhoon actually does when it arrives on a coastline, and Kong-rey is what trained the operational forecasters to take Jangmi's eye seriously. Part 8. Super Typhoon Kong-rey, October 31st, 2024. If you ask any operational meteorologist in the Western Pacific Basin what comes to mind when they see a tropical cyclone with an unusually large eye, they will tell you about Kong-rey. Super Typhoon Kong-rey made landfall at Chenggong in Taitung County on the eastern coast of Taiwan on the afternoon of October 31st, 2024. At landfall, the storm was a Category 4 equivalent on the Saffir-Simpson scale, with 1 minute sustained winds in the 190 to 200 km per hour range. The eye at landfall was measured at 46 miles, which is about 74 kilometers across. Some microwave satellite passes earlier in the storm's evolution had resolved the eye structure at closer to 100 kilometers. The pressure-wind relationship was unusual. The wind footprint was broader than the pressure would have predicted. The storm radius of strong winds extended outward more than 300 kilometers from the eye. Kong-rey was historically significant in several ways at once. It was the first typhoon in Taiwan's recorded history to make landfall after mid-October. The Western Pacific Basin's typhoon season climatologically winds down through October and November, with most years producing few or no late-season landfalls on Taiwan. Kong-rey violated that climatological expectation by arriving in the last days of October with a structure and intensity that would have been notable in the peak of the season. It was the largest storm-by-storm radius to hit Taiwan in nearly 3 decades, since Typhoon Herb in 1996. It produced widespread damage along the eastern Taiwan coast, with storm surge inundation, sustained eyewall winds, prolonged heavy rainfall in the mountainous interior, and significant agricultural and infrastructure losses. The death toll, while not catastrophic by the standards of the most lethal Pacific typhoons, was significant for the country, and the event was felt across all of Taiwanese public and political life for weeks afterward. Walk through what Kong-rey actually did at landfall, and you start to see why the operational forecast community remembers it the way it does. The eye wall took an extended period to pass over the landfall zone, with maximum sustained winds documented at multiple weather stations along the eastern Taiwan coast, holding above the Category 1 threshold for hours. The storm surge envelope was distributed across a wider geographic footprint than a Category 4 with a typical pinhole eye would have produced. The damage map after the event showed a broader band of significant impact, rather than a narrow concentrated corridor immediately under the eye. The post-event analysis emphasized that Kong-rey's structural footprint had delivered super typhoon damage geometry over an area more typical of a much larger storm. The reason this matters for the Jangmi forecast is that Kong-rey is the most recent operational case study in the basin for how a large-eyed Western Pacific typhoon interacts with a coastline at landfall. The lessons from October 2024 are fresh in the operational memory. The structural diagnostics that the forecasters use to recognize this class of storm are calibrated against the Kong-rey case. The damage geometry expectations are anchored against the Kong-rey case. The communications language that the meteorological community uses to describe a partly annular configuration to the public is calibrated against the Kong-rey case. When the Joint Typhoon Warning Center Prognostic Reasoning Bulletin on May 31st noted that Jangmi's eye had cleared to 70 nautical miles, the implicit context that every forecaster reading the bulletin understood was the Kong-rey context. This is the largest eye we have seen in the basin since that storm. This is the structural feature that we now know to be associated with broader wind footprints, longer durations of maximum sustained winds at any single point, and damaged geometries that exceed the textbook expectations for the category. The bulletin did not need to say all of that out loud. The forecast community knew the comparison the moment the measurement was published. There is one important difference between Kong-rey and Jangmi that needs to be flagged carefully. Kong-rey was a Category 4 super typhoon. Jangmi is a Category 1. The eye comparison is structurally illuminating, but the wind speed comparison is not. The destruction that Kong-rey delivered at landfall was driven by Category 4 winds, which are roughly twice the speed of Jangmi's current Category 1 winds, and, because wind energy scales as the cube of velocity, deliver something like 8 times the kinetic energy per square meter of exposed surface. Jangmi is not going to deliver Kong-rey scale destruction on Okinawa. The wind energy is not there. What Jangmi is going to deliver, and what the Kong-rey comparison illuminates, is the spatial and temporal geometry of how Category 1 winds are distributed across the landfall coastline. The wider eye means a wider footprint. The wider footprint means a wider area exposed. The wider area exposed means a larger total population in the maximum wind envelope. The longer eye wall passage time means a longer duration of sustained maximum winds at any single point. The longer duration means more cumulative loading on structures. The cumulative loading means a higher fraction of marginal infrastructure reaches failure thresholds. All of those effects scale with the eye geometry, not with the wind speed. They apply whether the storm is Category 1 or Category 4. They are the structural consequences of having a large eye, independent of the intensity of the eye wall winds. Kong-rey delivered them at Category 4. Jangmi is going to deliver them at Category 1. The total destruction will be lower, but the geographic distribution and the temporal duration will be similar to what the basin saw in Taiwan 18 months ago. The forecasters know this. The emergency management coordinators know this. The communications language that the Japan Meteorological Agency is using in its public advisories has been calibrated by what the basin learned from Kong-rey. The expectation envelope for tomorrow evening's landfall on Okinawa has been shaped by what the operational community absorbed from October 2024. Kong-rey is what trained the operational community to take Jangmi's eye seriously, and the lessons from October 2024 are what they are applying right now to June 2026. The recovery from Kong-rey took weeks. The Taiwanese government deployed military engineering units to restore the affected infrastructure. The agricultural losses in the eastern coastal counties extended well into the following spring planting season. The tourism industry on the eastern coast, which had been recovering from the broader pandemic-era disruptions, took another significant hit. The total economic impact was assessed by various Taiwanese government and academic analyses in the months following the event at approximately $1 to $2 billion in direct losses, with additional indirect losses across the broader supply chain and tourism sector. The death toll, while not catastrophic compared to the most lethal Pacific typhoons in the historical record, included casualties from storm surge inundation, from collapsing structures in the most vulnerable coastal communities, and from the kind of secondary hazards that always accompany a major typhoon transit, including landslides, river flooding, and infrastructure failures that affected emergency response capability. The post-event scientific analysis of Kong-rey was extensive. The Taiwanese Central Weather Administration and the National Taiwan University Department of Atmospheric Sciences both published detailed reanalyses of the storm's structural evolution, with particular focus on the eye size anomaly and the unusual late-season timing. The Japan Meteorological Agency, which had been monitoring the storm in parallel with the Taiwanese authorities, contributed its own observational dataset to the international scientific community. The Joint Typhoon Warning Center, which had issued the operational forecast track and intensity guidance during the event, completed its standard post-event verification and case study documentation, with the Kong-rey case added to the operational training material that newer forecasters work through as part of their qualification. That body of post-event analysis is what trained the current generation of operational forecasters across the basin to recognize the structural diagnostics that Jangmi is now exhibiting. The pattern matching is not just theoretical. The Kong-rey analysis is fresh in the operational memory. The structural diagnostics are calibrated against that case, and the language the meteorological community is using to describe Jangmi today directly reflects the lessons learned from Taiwan 18 months ago. The communication discipline that the JMA has been showing in its public advisories, which has emphasized the structural anomaly without invoking alarm-toned language, is the kind of communications calibration that comes from having recently worked through a similar case and absorbed the lessons about how to convey unusual structural features to a public that is more accustomed to thinking about tropical cyclones in terms of categories and wind speeds rather than in terms of eye geometry and footprint distribution. That is why this video is being made today. That is why this storm deserves a 2-hour deep dive. That is why a Category 1 Pacific typhoon, which would normally be a routine basin event, is being treated as a structurally important case that needs to be understood beyond just the wind speed and the central pressure. Because the basin has learned, the hard way, that some storms hit harder than their category numbers say they should. Kong-rey was the lesson. Jangmi is the test. Part 9. The Kyushu Industrial Cone. After Okinawa, the storm goes to Kyushu, the recurvature track that the Joint Typhoon Warning Center and the Japan Meteorological Agency have converged on takes Jangmi northeast from the Ryukyu chain, accelerating along the path of the mid-latitude westerlies, parallel to the southern coast of the Japanese home islands. The geographic targets along that track in order are the Amami Islands, southern Kyushu, the Shikoku coast, the southern Honshu coast, and finally the Tokyo-Kanto plain. Each of those targets has its own exposure profile. The most economically consequential of them, the one that puts national priority industrial infrastructure into the operational forecast cone, is Kyushu. Kyushu is the southwesternmost of the four main Japanese home islands. Its population is approximately 13 million people. Its principal cities are Fukuoka, Kitakyushu, Kumamoto, Kagoshima, Nagasaki, and Oita. Its economy includes agriculture, fishing, tourism, port logistics, automotive manufacturing, chemical processing, and, increasingly over the last 5 years, advanced semiconductor fabrication. The semiconductor cluster in Kyushu has been the focus of intentional Japanese government industrial policy since approximately 2021, when the Ministry of Economy, Trade and Industry began coordinating a national strategy to reshore advanced chip-making capability after decades of relative decline in the Japanese semiconductor industry. The flagship project of that strategy is the Taiwan Semiconductor Manufacturing Company's first fabrication facility in Japan, a joint venture called Japan Advanced Semiconductor Manufacturing, or JASM, which began production in late 2024 at a site in Kikuyo, Kumamoto Prefecture. The JASM facility is not the only semiconductor operation in Kyushu, but it is the most visible and the largest. Sony's image sensor fabs in the Kumamoto area have been in operation for years and have been expanding. A network of supplier and back-end assembly operations have grown in tandem with the broader cluster. The Industrial Info Resources Tracking Database, which monitors capital projects across the Japanese industrial sector, reports 116 active capital projects in Fukuoka Prefecture alone as of late May 2026, with a total investment value of $14 billion United States dollars. Of those, 50 are categorized as industrial manufacturing projects with a combined investment value of $10.5 billion. The Kyushu Industrial Cone, taken as a whole, is one of the most capital-intensive regional industrial development zones in Asia, outside of Taiwan and South Korea. Now picture what happens when a recurving Pacific typhoon sweeps across that cone. The first thing to understand is that the fabs themselves are not the principal vulnerability. Modern semiconductor fabrication facilities are built with extraordinary attention to environmental risk, including typhoons and earthquakes. They have on-site backup power generation in the form of large diesel generator banks and uninterruptible power supply systems that can ride through grid outages of hours to days. They have structural designs that are rated for typhoon-force winds and seismic events. They have water supply redundancy, with on-site reservoirs and treatment plants that can buffer against municipal water disruptions. The fabrication processes themselves run inside clean rooms that are sealed against the outside environment, and the most sensitive equipment, the lithography scanners and the etch chambers and the deposition tools, is installed in vibration-isolated enclosures that further buffer it from external disturbance. A fab is not going to be destroyed by a Category 1 typhoon. The capital investment in the structural envelope ensures that. What is vulnerable is the logistics. The fabs run on just-in-time supply chains that move silicon wafers, photoresist chemicals, lithography masks, precursor gases, and a long list of other inputs into and out of the facility on a continuous basis. Many of those inputs come into Japan through the port system, with Hakata in Fukuoka and Kitakyushu being the primary northern Kyushu ports for industrial freight, and Yatsushiro in central Kyushu being a secondary hub. The output, finished wafers shipped to customers worldwide, also goes through those same ports. When a typhoon hits, the ports close, crane operations stop, container ship arrivals and departures are suspended, the dwell time on existing inventory in the port stacks increases. The just-in-time logistical chain that the fabs depend on is interrupted, not for hours, but for 48 to 72 hours in most cases, sometimes longer if the storm produces significant infrastructure damage to the port facilities themselves. Aviation is the other choke point. Japan's air freight infrastructure handles a significant share of the high-value, time-sensitive semiconductor shipments that move in and out of the country. The major airports affected by a Kyushu typhoon landfall include Fukuoka Airport, Kumamoto Airport, Kagoshima Airport, and Nagasaki Airport. All of them suspend operations during major typhoon transits, typically for a window of 12 to 24 hours around the closest approach. Some suspensions extend longer if there is damage to the airport facilities or if the recovery operations take time. The cascading effect across the global semiconductor logistical chain is real, even if it is rarely visible outside the industry's internal supply chain management systems. The implication for the Jangmi event specifically is that the storm does not have to destroy a fab to hurt the semiconductor industry. It just has to delay the wafers, a 48-hour port closure at Hakata, a 36-hour suspension of Fukuoka Airport, a 72-hour dwell time increase on inbound chemical and gas precursor shipments. The kind of compound disruption that any major Kyushu typhoon produces is going to ripple through the global semiconductor supply chain in ways that the customers downstream from JASP and the Sony Kumamoto fabs are going to feel over the following weeks. The structural anomaly we have been describing, the wider eye and the longer duration of maximum sustained winds, may extend the port closure windows by several hours beyond what a textbook Category 1 would produce, which would amplify the supply chain disruption in proportion. There is a second economic exposure beyond semiconductors that is worth flagging. Kyushu hosts a significant share of Japan's automotive manufacturing capacity, including Toyota assembly plants and a network of parts suppliers that feed into the broader Japanese automotive sector. The Mazda headquarters and a substantial portion of Mazda's domestic production are located in nearby Hiroshima, just across the Kanman Strait from northern Kyushu. The chemical and petrochemical industry in Kita-Kyushu and the Kashima coastal complex extends a manufacturing footprint that includes steel, ceramics, and high-purity industrial gases. The Kyushu industrial complex, taken in its full breadth, represents something approaching 10% of the entire Japanese manufacturing output by value. A direct typhoon hit, even at Category 1 intensity, has cascading consequences across multiple sectors of the Japanese industrial economy. None of this is meant to imply that Jangmi is going to be an economic catastrophe for Japan. It will not be. The Japanese industrial sector is deeply experienced in managing typhoon disruptions, and the operational continuity protocols that the major firms have built up over decades will absorb most of the impact. But the storm is going to be felt in the supply chains. The wafer flow through Hakata is going to be disrupted. The just-in-time inventories at the Sony fabs are going to be tested. The aviation cargo flowing through Fukuoka Airport is going to be delayed. And the customers downstream, who range from the major American hyperscalers buying memory and logic chips through the European automotive sector buying Sony image sensors, are going to feel the secondary effects over the following weeks. The recurvature track is putting one of the most economically consequential regional industrial clusters in Asia directly under the storm cone for 48 hours. The structural anomaly in the eye is going to extend the disruption window beyond what the textbook would predict. The downstream supply chain consequences are going to be measurable but manageable, and the Japanese industrial system, which has been doing this since the original Meiji-era industrial build-out, is going to absorb the impact and move on. There is a specific historical case from the Japanese industrial response to typhoon impacts that is worth remembering as Jangmi approaches. In October 2019, Typhoon Hagibis made landfall on the Tokyo-Kanto plain as one of the most powerful typhoons to affect mainland Japan in decades. The storm caused widespread flooding across central Honshu, killed nearly 100 people, and disrupted industrial operations across the country. The Japanese semiconductor and electronics industry, which at that time was less geographically concentrated than the current Kyushu cluster, nonetheless experienced significant supply chain disruption that took several weeks to fully resolve. The lesson from Hagibis was the importance of pre-positioning inventory buffers and of maintaining redundant logistical pathways through multiple ports and airports, rather than relying on single choke points. The Japanese industrial sector internalized that lesson, and the operational continuity protocols that the major firms now run are more sophisticated than they were 6 years ago. The Kyushu industrial cluster, which has grown significantly since Hagibis, has been built with that institutional memory in mind. The fabs have backup logistical routes. The port operators coordinate with the shippers to pre-position inventory across multiple facilities. The aviation cargo handlers have rolling alternative routes through multiple Japanese airports and through international hubs like Incheon, Hong Kong, and Singapore. The other element of the Japanese industrial response that is worth flagging is the role of the broader supply ecosystem beyond the headline manufacturers. The semiconductor cluster in Kyushu is supported by a long tail of supplier firms, including precision tooling manufacturers, specialty chemical producers, photoresist suppliers, and equipment maintenance contractors, Many of these supplier firms are headquartered or have major operations in the Kyushu region itself, which means that a Kyushu typhoon affects not just the headline fabs, but the entire ecosystem of firms that support those fabs. The disruption window for the headline manufacturers may be 48 hours, but the disruption window for the supplier ecosystem can extend significantly longer if the smaller firms have less redundancy in their own operations. This is one of the structural vulnerabilities of geographic concentration in advanced manufacturing clusters. The cluster benefits from co-location during normal operations but pays a concentrated penalty during regional disruption events. For Jangmi specifically, the supply ecosystem implications are going to be tracked closely by the major customers of the Kyushu semiconductor and automotive output over the following weeks. The hyperscalers in the United States that purchase memory and logic chips from JASM and from Sony. The European and American automotive OEMs that purchase image sensors from Sony for advanced driver assistance systems. The Japanese domestic electronics manufacturers that purchase precision components from the broader Kyushu supplier network. All of those customers will be receiving operational continuity advisories from their suppliers over the next 48 hours, and the secondary effects on the customer's own production schedules will emerge over the following 1 to 3 weeks. After Kyushu, the storm goes to the Tokyo-Kanto plain. By the time it gets there, the system will have weakened to severe tropical storm intensity and begun the process of extratropical transition. The Tokyo exposure is principally transportation and aviation, with the Shinkansen high-speed rail network historically taking protective suspension postures during severe typhoon impact, and Narita and Haneda international airports having a documented pattern of mass cancellations during typhoon transits of the Kanto plain. The damage profile in Tokyo is going to be less severe than the Okinawa or Kyushu impacts, because the storm will have weakened significantly by the time it arrives. But 38 million people live in Greater Tokyo, and even a weakened typhoon transiting that population centre is a significant operational event for the world's largest urban agglomeration. By Friday, June 5th, the system will have completed extratropical transition and exited northeastward into the open Northwest Pacific. The aftermath will be a 5-day window of cleanup, damage assessment, infrastructure repair, supply chain recovery, and post-event analysis across the Japanese government and the international meteorological community. The forecasters will go back through the satellite imagery and the surface observations and the model performance and write up the case study that will go into the operational knowledge base for the next storm with a wide eye and a recurving track. The Kong-rey case will be updated with the Jangmi case. The basin's institutional memory will grow. That is what is coming. That is the operational reality of the next 5 days for the Western Pacific Basin. But there is one more layer of context that has to be put on the table before we get to the watch window, because the Jangmi event is not happening in a climatological vacuum, and the broader 2026 season is itself developing in a way that suggests this storm may not be the last unusual one we see this year. Part 10. The El Niño Transition and the 6th Storm of 2026. The climate state of the Pacific Ocean in May 2026 is in transition. The Oceanic Niño Index, which is the primary metric the United States National Oceanic and Atmospheric Administration uses to track the El Niño Southern Oscillation Cycle, measures the 3-month running average of sea surface temperature anomalies in the Niño 3.4 region of the Central Tropical Pacific. The most recent value for the February through April 2026 season was positive 0.11 degrees Celsius above the long-term average. That number is barely above the neutral threshold of 0.5 degrees, but it represents a substantial shift from where the index was just 6 months earlier. In the October through December 2025 season, the value was negative 0.55, solidly in the La Niña range. The 2-season swing from negative 0.55 to positive 0.11 is positive 0.66 degrees, which is a relatively rapid transition by historical standards. What that swing represents is the formal exit from the La Niña conditions that dominated the second half of 2025 and the beginning of a transition toward El Niño conditions that may be reached later in 2026 or in 2027. The NOAA Climate Prediction Center has been issuing El Niño watch language in its monthly ENSO diagnostic updates, with elevated probability of El Niño onset across the second half of the calendar year. The Pacific is warming. What that has to do with Western Pacific typhoons is a topic that has its own substantial body of research, and the relationship is more nuanced than the headlines often suggest. The general pattern is that El Niño years tend to produce slightly more Western Pacific typhoons in absolute count, and tend to shift the formation regions and the recurvature patterns relative to neutral or La Niña years. Specifically, El Niño years tend to favour typhoon formation further east in the basin, with longer trajectories and a higher proportion of storms recurving away from the Asian mainland and impacting Japan rather than the Philippines or Vietnam. La Niña years tend to favour formation further west, with shorter trajectories and a higher proportion of storms impacting Southeast Asia. The transition years, when the index is moving from La Niña toward El Niño but has not yet reached the El Niño threshold, can sometimes produce early season activity that is anomalous relative to climatology. The fact that Jangmi is the sixth named system of the 2026 Western Pacific season is itself a modestly above average count for the May 31st date. The climatological average through the end of May is approximately 3 to 4 named systems. 2026 is running about 2 storms ahead of the average pace. That is not a dramatic deviation, but it is a deviation in the direction that the ENSO transition would predict. Whether the structural anomaly we have been describing in Jangmi is itself a signal of the broader climate transition is an open question. The relationship between ENSO state and tropical cyclone structure is not well established in the literature. There is good evidence that ENSO modulates frequency, formation region, and large-scale steering, but the connection to specific structural features like eye diameter and annular configuration is much less robust. Jangmi may be a structurally interesting storm that happens to occur in a transitioning climate state for unrelated reasons. Or the structural anomaly may be one early visible signature of a 2026 season that is going to produce more storms with unusual configurations. The honest scientific answer is that we do not yet know, and we will not know for many years, because the question requires the accumulation of a much larger data set of structural observations across multiple El Niño transition cycles to extract any statistically significant signal. What we do know is that the 2026 Pacific season is starting in a way that has the operational community paying attention. The structural anomaly Jangmi is exhibiting is something the basin has not seen in 18 months, and the climatological context the storm is forming in is shifting in ways that historically have produced more rather than fewer anomalous events. There is a piece of historical context here that is worth understanding, because the ENSO-typhoon relationship has been studied for more than a century, and the basic framework that operational climatologists use is fairly well established. The original observational work on ENSO modulation of Western Pacific typhoon activity dates back to the early to mid-20th century, when Japanese, Filipino, and American meteorologists began noticing systematic shifts in typhoon formation patterns that correlated with sea surface temperature variations in the central tropical Pacific. The modern statistical framework, which uses standardized indices like the Niño 3.4 region and the Southern Oscillation Index, was largely developed in the 1960s and 70s as the broader teleconnection literature emerged. The contemporary understanding, codified in the World Meteorological Organization's various reports, and in the published reviews that the National Center for Atmospheric Research and the Geophysical Fluid Dynamics Laboratory and similar institutions have produced over the last 2 decades, is that ENSO is one of several large-scale climate modes that modulate tropical cyclone activity, but is not the only one and is not always the dominant one in any given season. The other major climate modes that modulate Western Pacific typhoon activity include the Indian Ocean Dipole, the Madden-Julian Oscillation, the Western Pacific Monsoon, and the longer-period Pacific Decadal Oscillation. Each of these modes operates on different timescales and affects different aspects of the typhoon climatology. The Madden-Julian Oscillation, which is a roughly 30 to 60-day oscillation in tropical convective activity, can modulate the cyclogenesis rate on weekly to monthly timescales. The Indian Ocean Dipole can affect the steering patterns and the cross-basin teleconnections. The Pacific Decadal Oscillation can produce multi-decadal shifts in the average frequency and intensity of basin activity. Any individual season is the integrated effect of all of these modes operating simultaneously, plus the influences of the broader background climate state, plus the random variability that always accompanies a chaotic system like the global atmosphere. For 2026 specifically, the ENSO transition is the most visible and most easily quantified of these climate modes, but it is not the only one operating. The Madden-Julian Oscillation has been in active phases over the Western Pacific during much of the spring, which has likely contributed to the modest above-average early season activity in the basin. The Indian Ocean Dipole has been in roughly neutral configuration. The Pacific Decadal Oscillation has been in a phase that historically correlates with slightly elevated Western Pacific typhoon activity. The integrated effect of these various modes is what produces the climatological backdrop against which any individual storm, including Jangmi, has to be interpreted. The structural anomaly Jangmi is exhibiting may be one early visible signature of a 2026 Pacific season that is shifting against the climatological baseline. It may also be a single curious data point with no broader implications. The next several months will be informative either way. The operational forecast community is watching closely. Part 11. The Energy Budget Wall. Whenever a major weather event makes the news cycle, a parallel narrative develops on social media that proposes alternative explanations for what is happening. This is not unique to typhoons. Hurricanes, earthquakes, volcanic eruptions, blizzards, droughts, all of them attract speculation about hidden mechanisms, suppressed information, or deliberate manipulation by various actors. The specific actors and mechanisms vary depending on the event and the audience, but the underlying pattern is consistent. A natural event happens. The official scientific community describes it using the standard physical mechanisms. A parallel community proposes that the official explanation is incomplete or false, and offers an alternative that often involves intentional human action. For Jangmi specifically, the alternative narratives that have appeared in the social media discourse so far cluster into three main framings. The first is that the unusually large eye is evidence of intentional weather modification, either through cloud seeding by aircraft, through ionospheric heating using facilities such as the High-Frequency Active Auroral Research Program in Alaska, or through other proposed mechanisms. The second is that the typhoon track has been deliberately steered toward the United States military installations on Okinawa, or toward the Kyushu semiconductor cluster. The third is the Okinawa can't catch a break compound event framing we already addressed. The clean way to handle these narratives is not to dismiss them as paranoid, because the underlying observations are often real. The eye is unusually large. The track does pass close to the military installations and the industrial cluster. The compound seismic and typhoon hazard is real. The narratives latch onto real features. Where they go wrong is in the proposed mechanism. The mechanism does not exist at the scale required. Let's do the energy budget arithmetic on the weather modification claim, because it is the cleanest single rebuttal, and it applies across the entire class of intentional storm creation hypotheses. A mature typhoon dissipates kinetic energy at a rate that the published literature on tropical cyclone energetics places in the range of 10 to the 14th to 10 to the 15th watts. That is 100 trillion to 1,000 trillion watts of continuous power dissipation. The total energy throughput of a single Category 4 storm over the course of its life is on the order of 10 to the 18th or 10 to the 19th joules, which is comparable to a few weeks of total global human energy consumption from all sources combined. The HAARP facility in Gakona, Alaska transmits radio frequency energy at a peak power of approximately 3.6 megawatts, 3.6 times 10 to the 6th watts. The energy ratio between a mature typhoon's continuous dissipation and HAARP's peak transmitted power is approximately 15 orders of magnitude. That is a factor of 1 followed by 15 zeros. There is no plausible mechanism by which the smaller energy source can drive the larger energy system. The wattage difference alone rules out the hypothesis at the most basic physical level. There is no clever engineering trick that bridges 15 orders of magnitude in power. The mechanism does not exist at the scale required. The cloud seeding hypothesis is more carefully grounded in real meteorological technique, because cloud seeding is in fact a real intervention that has been deployed for decades in various contexts. The most authoritative recent review of cloud seeding effectiveness is the Rauber et al. 2019 paper in the Bulletin of the American Meteorological Society, which surveyed the published evidence on wintertime orographic cloud seeding programs and concluded that, under favorable conditions, the technique can produce approximately 5 to 15% enhancement of precipitation in existing cloud systems. That is a real effect. It is also, by the author's explicit framing, an enhancement of existing precipitation, not a creation of new storms from clear sky. Cloud seeding cannot manufacture a tropical cyclone. It cannot intensify one beyond what the underlying environmental conditions would allow. It cannot steer one along a preferred track. The technique simply does not have those capabilities. The published literature is unambiguous on this. The track steering hypothesis is the easiest to dispatch because it requires the proposed manipulators to override the integrated effect of every global atmospheric observation system simultaneously. Tropical cyclone tracks are steered by the position and amplitude of the subtropical ridge and the location of the mid-latitude jet stream. Both of those features are measured continuously by satellite, radio sonde, surface station, and aircraft observation networks operated by every major national meteorological service in the world. The European Centre for Medium-Range Weather Forecasts, the United States National Weather Service, the Japan Meteorological Agency, the China Meteorological Administration, the United Kingdom Met Office, the Australian Bureau of Meteorology, and dozens of others all run independent numerical weather prediction models using the same shared observational data. When those models converge on a track forecast as they have for Jangmi, it is because they are all extracting the same atmospheric signal from the same shared observations. A coordinated falsification of the observational record across all of those national services in real time every 6 hours, with consistent results that all agreed independent researchers can verify, would be an undertaking of a scale that has no plausible operational basis. The most defensible reading of Jangmi remains the routine reading. A structurally interesting but climatologically familiar Western Pacific typhoon, doing what the steering pattern is making it do. An unusually large eye that the published literature on annular hurricanes and eye-wall replacement cycles provides established vocabulary to describe. A track that follows the standard recurvature pattern for early summer storms in the basin. An intensity that holds within the Category 1 range as the storm interacts with marginally favourable environmental conditions over warm sea surface temperatures. A landfall envelope that the operational forecast community is treating with appropriate seriousness, given the structural anomaly, but without invoking any extraordinary mechanism beyond the physics that the published research already documents. There is one more piece of context worth adding here, because it speaks to why the alternative mechanism narratives gain traction, even when the underlying physics is so clearly against them. The pattern that researchers in the science communication field have documented across many natural event contexts is that the alternative narratives tend to arise in situations where the official explanation feels incomplete, where the official communication is perceived as condescending or distant, or where the official sources have a history of having been wrong in the past, in ways that the affected community remembers. None of those preconditions apply particularly strongly to the Western Pacific Typhoon Basin, where the Japan Meteorological Agency and the Joint Typhoon Warning Center have decades of operational track records that include very few major forecast failures. But the alternative narratives appear anyway, because they fill a different need than the official explanation does. They provide a sense of agency and explanation in the face of an event that is, by its nature, beyond human control. They offer the consolation of believing that someone is in charge, even if that someone is a hostile actor, because the alternative belief that the storm is simply a feature of the planet's atmospheric heat engine is more existentially unsettling than the conspiracy. The honest scientific response to these narratives is not to mock them, but to explain, patiently and clearly, why the proposed mechanisms do not work, which is what we have just done. The energy budget, the cloud seeding effectiveness limits, the observational network that makes track steering manipulation impossible, the published literature that documents the actual mechanisms that produce storms like Jangmi. All of these are available to anyone who wants to look at them. The information is not hidden. The mechanism is well understood. The official explanation is, in this case, also the best explanation. The most defensible reading of Jangmi remains the routine reading, a structurally interesting but climatologically familiar Western Pacific typhoon, doing what the steering pattern is making it do, exhibiting an eye configuration that the published literature already names and explains, and arriving on a coastline whose preparation systems and historical experience are well suited to absorb the impact even when the structural anomaly extends the operational window beyond what a textbook event would produce. Which brings us to what the next 24 hours are actually going to look like and what the operational community is watching for. Part 12. The 24-hour watch window. The next day is when this story actually happens. By 6 o'clock Universal Time on June 1st, which is 3 in the morning Japan time, the eye of Typhoon Jangmi will be roughly 5 to 6 hours from its closest point of approach to Okinawa. The outer rain bands will already be impacting the southern Ryukyu chain. The Takara Islands and the Amami Islands further northeast will be in the storm's approach corridor. The Japan Meteorological Agency will have stepped up its typhoon advisories to their most active phase. The United States military installations on Okinawa will have transitioned from TCOR 2 to TCOR 1 caution, indicating that destructive winds are anticipated within 12 hours. The population on the main island will be sheltered in place, or completing the last hour of pre-storm preparation. Between now and that moment, the operational forecast community is going to be watching a specific set of observable signals to determine which of the structural evolution scenarios is actually playing out. The most important signal to watch is the microwave satellite imagery. Microwave sensors on polar orbiting satellites can see through the upper cloud deck to image the structure of the eye wall itself, which is invisible to standard visible and infrared imagery once the storm builds enough cirrus canopy overhead. The Defense Meteorological Satellite Program platforms, the Global Precipitation Measurement Core Observatory, and the Special Sensor Microwave Imager Sounder pass over the typhoon every few hours and produce images that show whether the inner core is contracting, holding steady, or expanding. If the operational community sees an inward contracting secondary eye wall in the next 12 to 24 hours, the storm is undergoing an eye wall replacement cycle that may briefly intensify it as the new tighter eye consolidates. If the eye wall structure holds steady at its current wide configuration, the storm is going to arrive on Okinawa as the structurally anomalous Category 1 we have been describing throughout this script. The second signal is the JTWC update cadence. The Joint Typhoon Warning Center issues prognostic reasoning bulletins every 6 hours, and the discussion language inside those bulletins shifts in subtle ways as the forecaster's confidence in various scenarios changes. A bulletin that uses the word consolidating is signaling that the operational community sees evidence of eye wall replacement. A bulletin that emphasizes the steady-state intensity guidance is signaling that the partly annular interpretation is being maintained. The next 4 bulletins, covering the windows from now through closest approach, will tell us how the operational reading of the storm is evolving. The third signal is the surface observations from Okinawa weather stations as the eye wall approaches. The wind speeds and gust durations recorded at the official Japan Meteorological Agency weather stations on the main island and at the United States military installations will provide ground truth data on what the storm is actually delivering. A textbook Category 1 would produce sustained 90 to 100 km/h winds for a window of about 90 minutes at peak. The structural anomaly we have been describing would extend that window to as long as 5 hours at any single station under the eye wall path. The difference will be visible in the wind speed time series within the first 3 hours of the eye wall arrival. The fourth signal is the rainfall accumulation as the outer bands and then the eye wall move ashore. The 400mm forecast accumulation for the southeastern coast of mainland Japan is the integrated total over the duration of the event, but the leading-edge rainfall on Okinawa over the first 12 hours will tell us whether the storm is producing more or less precipitation than the typical Category 1 envelope. A wider, slower eye wall with longer duration of exposure produces more cumulative rainfall over any single point, which is one of the reasons inland flooding is a particular concern for partly annular configurations. The fifth signal is the Kyushu industrial response. The port operators at Hakata, Kitakyushu and Yatsushiro will issue port closure notices on a schedule driven by the forecast arrival of severe weather conditions. The major semiconductor and automotive firms will issue operational continuity advisories to their supply chain partners. The aviation authorities will begin issuing precautionary flight suspension notices. The cadence and timing of those notices will indicate how seriously the industrial community is taking the storm's approach, which is itself a real-time indicator of the operational community's confidence in the severity forecast. The sixth signal is the Tokyo Transportation System posture. The Japan Rail Group will begin issuing Shinkansen service notices in advance of the storm's expected arrival in the Kanto Plain. The Tokyo Metro will begin pre-positioning maintenance crews and reviewing flood mitigation protocols. Narita and Haneda will begin issuing rolling flight cancellation notices to airlines. By Thursday morning Japan time, the transportation rhythm of the Tokyo metropolitan area will reflect the operational community's assessment of the storm's likely impact on the Kanto Plain. There is a seventh signal that is worth flagging, because it operates on a longer timescale than the immediate landfall window and may be the most consequential indicator of what the storm actually means. That signal is the post-event scientific community response. In the days and weeks following the storm's exit from the basin, the operational and academic meteorological communities will produce a series of reanalysis products, conference presentations, and eventually peer-reviewed publications that examine the structural evolution of Jangmi in detail. The Japan Meteorological Agency will publish its standard post-event verification reports, the Joint Typhoon Warning Center will complete its operational case study documentation. The university research groups in Japan, Taiwan, the Philippines, and at relevant institutions in the United States and Europe will begin the slower process of academic analysis that will eventually produce the published literature on what Jangmi was and what it tells us about the broader population of Western Pacific tropical cyclones in the current climate state. That post-event scientific response is where the broader question of whether Jangmi represents a single curious data point or the leading edge of a pattern will begin to be answered. The reanalysis products will quantify the eye geometry through the storm's life cycle with more precision than the operational products allow. The structural diagnostics that operational forecasters use to recognize the partly annular configuration will be refined against the Jangmi case. The communications language that the meteorological community uses to describe structural anomaly to the public will be updated to incorporate the lessons of this event, and over the longer term, the published literature on the basin's tropical cyclone population will incorporate the Jangmi case into the statistical record that future climate-related studies will draw on. The watch window for the storm itself is 24 hours. The watch window for what the storm means in the broader scientific and operational context is several years. All of these signals will be observable. All of them will be reported in real time by various combinations of official advisories, news media coverage, and social media discussion. Anyone who wants to follow the storm in detail over the next 4 days will have access to a continuous stream of operational information from the world's most sophisticated typhoon forecasting infrastructure. The Joint Typhoon Warning Center will be updating every 6 hours. The Japan Meteorological Agency will be updating on a similar cadence. The Zoom Earth platform, the Weather Underground tracker, the Stars and Stripes military weather coverage, the Spaceflight Now style independent meteorology reporting, all of them will be providing continuous updates as the storm makes its run across the Japanese archipelago. The next 24 hours will tell us whether Jangmi tightens its eye and finds another category, or whether it holds at Category 1 with a Category 4 wind footprint. Either way, what arrives on Okinawa tomorrow evening is going to be unusual, and by the time the storm has completed its run across Japan and exited northeastward into the open Pacific, the basin will have a new case study added to its institutional memory, sitting alongside Kong-rey 2024 and the longer historical record of partly annular Western Pacific typhoons. That is the operational reality of the watch window. What it means in the broader frame, what it tells us about the kind of typhoons this basin is producing in the current climate state, what it adds to the longer story of how the world's most active tropical cyclone basin is changing over the decades, is the question we have to land on as we close. Part 13. The question we're holding. A typhoon does not normally exhibit a 130-kilometer eye while sustaining only Category 1 winds. The configuration is rare. The published research on annular hurricanes and on eye wall replacement cycles provides the vocabulary to describe it, but the underlying frequency of this kind of structural anomaly in the Western Pacific Basin is not high. The basin has produced thousands of typhoons in the satellite era. A small minority of them have exhibited the structural features that Jangmi is showing right now. Kong-rey in 2024 was the most recent comparable case, and even Kong-rey was not a textbook annular system, although it shared enough features to be informative. Before Kong-rey, you have to go back several years to find a Western Pacific storm with a comparable eye configuration. The class is not extinct, but it is uncommon enough that each new case attracts the close attention of the operational forecast community across the basin. What makes Jangmi different is the combination. The wide eye, on its own, would be noteworthy. The Category 1 intensity on its own would be routine. The two together produce a storm that has the spatial structure of a major typhoon and the wind energy of a minor typhoon, arriving on a coastline that has built its preparation infrastructure around the assumption that those two metrics scale together in a predictable way. The wider eye distributes the eye wall winds across a wider footprint. The wider footprint exposes more coastline to the maximum sustained winds at any single moment. The longer eye wall passage time, which our geometry calculations showed could exceed 5 hours at the storm's current configuration, extends the duration of maximum sustained winds at any single point, well beyond what a textbook Category 1 envelope would produce. The wider storm surge generation footprint inundates a wider geographic distribution of low-lying coastal infrastructure. A Category 1 typhoon with the eye structure of a Category 4 Super Typhoon delivers Category 1 winds in a Category 4 spatial distribution. That combination is what the world's typhoon forecasters are bracing for at landfall. It is not going to produce Category 4 destruction. The wind energy is not there. But it is going to produce damaged geometry and operational disruption envelopes that exceed the textbook expectations for a Category 1 event. The bases on Okinawa will absorb the impact. The civilian population will shelter through it. The Kyushu industrial cluster will manage the supply chain interruption. The Tokyo transportation system will execute its standard typhoon protocols. Japan will do what Japan does, which is what Japan has always done, which is take the typhoon and keep going. But the basin will learn something from this storm. The operational case study that comes out of Jangmi will be added to the operational case study that came out of Kong-rey, which will be added to the longer record of large-eyed Western Pacific typhoons going back through the satellite era. The institutional knowledge of how this class of storm behaves will grow. The communications language that the meteorological community uses to describe structural anomaly to the public will be refined. The structural diagnostics that the forecasters use to recognize the partly annular configuration in real time will be sharpened. The next time a storm with this combination of features appears in the basin, the operational response will be a little better calibrated than it was this time, because Jangmi will have happened and the case study will be in the file. The deeper question, the one that this video has been quietly building toward across the last 2 hours, is whether Jangmi's anomaly is a single curious data point in the history of the Western Pacific Basin, or whether it is the first visible signature of a 2026 season that may force a re-examination of how this basin is producing tropical cyclones in the current climate state. The honest scientific answer is that we do not yet know. The relationship between climate change and tropical cyclone structure is a much harder question than the relationship between climate change and tropical cyclone intensity, and even the intensity question is still under active research with substantial uncertainty in many of the projections. The most authoritative recent review, the Knudsen et al. 2020 assessment published in the Bulletin of the American Meteorological Society, identifies a robust signal toward higher peak intensities and toward a poleward shift in the latitude of peak intensity. But the signals on storm size and on eye diameter are much less robustly identified, in part because the historical satellite record of consistent microwave observations of eye structure is short and inhomogeneous. Jangmi does not by itself establish a trend. One storm with an unusual eye, in one early summer week of one transitioning ENSO year, in one basin among the global tropics, is not a climate signal, it is a single data point. The next 10 storms, and the 10 after that, and the 10 after that, are what will establish whether the pattern Jangmi is exhibiting is becoming more common in the basin, or whether it remains a rare structural curiosity. The accumulation of evidence will take years. The conclusions, if they emerge, will be drawn slowly, with appropriate scientific caution, by researchers working on the multi-decade timescales that climate science requires. But Jangmi does sit comfortably inside the rising tail of a distribution that is being closely watched. The operational community is paying attention. The peer-reviewed research community is paying attention. The basin is paying attention. The storms of the next several years will tell us whether what we are seeing in Jangmi today is the start of a pattern or the latest instance of a long-standing rare configuration. And in the meantime, the storm is moving. The eye is open. The track is locked. The recurvature is forecast. The closest approach to Okinawa is hours away. The Kyushu industrial cone is in the path. The Tokyo transportation system is preparing. The bases are at Tekor 2. The advisories are stepping up. The ferries are coming in. The ports are getting buttoned up. The fabs are checking their backup generators. The supply chains are bracing for the disruption window. The emergency management coordinators are leaning forward. The forecast community is watching the satellite microwave passes for signs of secondary eye wall contraction. The world is doing what the world does when a typhoon of this kind appears in this basin at this time of year. It is preparing. Somewhere over the Philippine Sea, a calm circle 130 kilometers across is rotating north toward Japan. The hole in the clouds anyone can see from space. The eye that should not be that wide on a Category 1 storm. The structural anomaly that has the operational community paying close attention. The storm that is going to teach us something. The largest single thing that should stay with you from these last 2 hours is this. A storm's category number is a useful first-order approximation of how much damage that storm is going to deliver, but it is not the whole story. The category number measures the wind speed. It does not measure the geometry. It does not measure the duration. It does not measure the spatial distribution of the wind field. It does not measure the eye structure. Two storms with the same category number can deliver fundamentally different damage envelopes if their structural geometries are different. Most of the time, the category number is a reasonable summary of the operational hazard because most storms have eye structures that fall in the typical range for their intensity. But when a storm exhibits a structural anomaly, the category number becomes a misleading summary, and the operational community has to look past it to understand what the storm is actually going to deliver. Jangmi is one of those cases. Category 1 winds, Category 4 spatial distribution, a combination that the category number alone does not capture. That is the lesson the basin learned from Kong-rey 18 months ago, and the lesson the basin is going to refine from Jangmi over the next several days. The category number is the first thing to look at, but it is not the only thing to look at. The eye is what tells you whether the category number is a good summary, or whether you have to look past it. The eye is the diagnostic. The eye is the window into the storm's actual structure, and the eye, in this case, is 130 kilometers wide. What arrives at Okinawa tomorrow evening is going to be unusual. The only question is what we learn from it. And the answer to that question, like the answer to so many questions about the relationship between this basin and the climate state it is forming in, will only become clear in the slow accumulation of years. There is something almost meditative about watching a satellite loop of a tropical cyclone, especially one as structurally distinctive as this one. The slow rotation of the cloud field, the persistent dark circle at the centre, the outer rain bands curling inward through a perfect mathematical spiral, the whole thing turning and turning and turning across the warm tropical ocean, hour after hour, day after day, indifferent to anything that is happening on the ground beneath it. The storm does not know what an industrial cluster is. It does not know what a military base is. It does not know what a school district closure decision is. It does not know that the people on the islands below it are preparing, planning, sheltering, watching the same satellite loop from the other side of the screen. It is just a heat engine, drawing energy from the warm water below, releasing that energy in the form of motion and rainfall and pressure differentials, executing the same physics that produces every tropical cyclone in the world. The fact that this one is doing it with a 130-kilometer hole at its centre, instead of the more typical 30 or 40, is what makes it interesting to the people whose job is to study these systems. The eye is the diagnostic. The eye is the window into what is happening internally. The eye is what tells the forecasters that this storm is structurally unusual, that the operational expectations need to be calibrated against the wider footprint rather than against the textbook envelope, that the lessons of Kong-rey 18 months ago need to be applied to the case now arriving on Okinawa. That is what the next 40 hours are about. That is what the basin is going to be watching. That is what this video has been quietly building toward for 2 hours. Not the wind speed, although the wind speed matters. Not the central pressure, although the central pressure matters. Not even the track, although the track is what determines who feels the storm and when. What this video is about is the structure, the geometry, the wide eye on a Category 1 storm. The Category 1 winds in a Category 4 spatial distribution, the duration of the eye wall passage, the footprint of the maximum sustained winds, the kind of damage envelope that arrives when a storm hits harder, for longer, across a wider area than its category number says it should. That is the test that the basin is about to run. The test that the operational forecast community has been preparing for since they saw the eye start to clear over the weekend. The test that the institutional memory of the basin has been building towards since Kong-rey landed in Taiwan in October of 2024. The test that, by Friday, June 5th, the meteorological community will have absorbed into the next iteration of its operational understanding, the next case study in the training material, the next chapter in the long, slow accumulation of human knowledge about how the planet's atmosphere produces the most powerful weather systems on Earth. The hole in the clouds is moving. The basin is watching. The world is going to find out hour by hour, station by station, advisory by advisory, as the next several days unfold across the Japanese archipelago.